All of the assumptions that we've looked at in the context of the classical linear regression model so far have been concerned with investigating the properties of the disturbance terms. What I want to do now is to look at the possibility that we've actually formulated the wrong model. So all of the diagnostic tests that we've examined so far have assumed that the model is correct, and in some senses there is a problem with the residuals. But there are two possible errors that we could make where we've actually formulated the wrong model. The first error is where there's an important determinant of the variable y, but which we've left out of our regression model. So this will be the situation where we've omitted an important variable. So for example, suppose that we'd estimated a simple bivariate regression model including an explanatory variable x2t. But the data generating process for y, in fact, it includes also another explanatory variable which, for example, might be called x3t, but which we have not included in our model. We may have excluded this variable because we didn't know that it existed, maybe we couldn't get data on that variable, or maybe we thought that it wasn't very important. In any of those three cases, what would be the consequences for the properties of our OLS estimator if we'd actually excluded important variables from the model? Well, the consequences would be that the estimated coefficients on all of the other variables will be biased and inconsistent unless the excluded variable is uncorrelated with all of the included variables. Even if the excluded variable or excluded variables is or are uncorrelated with all of the included variables, then the estimate of the coefficient on the constant term will be biased. One implication of that is that any forecast we make from our model will also be biased or incorrect. Finally, if we omit an important variable from a regression model, the standard errors will also be biased. So we can see that omitting an important variable from a regression model is potentially one of the most serious errors that we could make in formulating our econometric model. What would happen, on the other hand, if we made exactly the opposite error? That is, we formulated a model that was in a sense too large. In other words, what would happen if we formulated a model that also included some irrelevant variables? So in that situation, our empirical model that we actually estimate would include extra variables that weren't present in the true data generating process for y. Well, in that situation, it turns out that the consequences are much less serious than the consequences from omitting an important variable. The consequences of including an irrelevant variable are that the ordinary least squares estimator will still be consistent and unbiased, but it will be inefficient. The reason that the ordinary least squares estimator is inefficient in the context of included irrelevant variables could be thought of as follows. If we include irrelevant variables in the model, then obviously the number of parameters that we're estimating, k, will increase. Therefore, for a fixed number of observations t, the value of the degrees of freedom, t minus k, will be reduced. If the value of the degrees of freedom t minus k is reduced, that means our estimate of the variance of the disturbances, sigma hat squared, which is the residual sum of squares divided by t minus k, will be correspondingly increased. We know that all of the standard error estimates for the intercept and the slope coefficients will be positively related to sigma hat squared or s squared. So therefore, if this goes up, it must be the case that the standard error estimates for all of the parameters in beta hat must also rise. So in the context of included irrelevant variables in a regression model, the coefficient estimates will still be okay. The only problem that will arise will be that the standard errors will be bigger than they otherwise would have been. And the reason that that occurs is that we'll be wasting degrees of freedom by trying to estimate these extra parameters that we don't really need to estimate. Given that the problem of including irrelevant variables is much less serious in practice than the problem of excluding relevant variables, this has an important implication for econometric model building philosophies. And in particular, if we have a set of candidate variables and we're not really sure whether those variables should be included in the regression model or not, if in doubt, then what we should do is include them in the model. because if we include them and they turn out not to be important in practice, the consequences of doing that will be much less serious than if we excluded variables but they turned out to be important and we didn't realise it. Of course, if we're in doubt, we can include the variables into the original regression model and then examine the t-ratios on those variables and subsequently delete any variables whose t-ratios are not statistically significant. So that's how we'd actually proceed in practice. Another implicit assumption that we make when we estimate regression models is that the parameters of those regression models are stable across the whole sample. Another way of saying that is, when we developed the multiple linear regression model, I said that in fact one thing we could do is to write out a separate equation for each of the observations. Whilst the equation for each observation is different in the sense that the values of the x's and the y's will be different for each observation, of course, embodied in that is the assumption that the parameters, that is the values of the betas, are the same for all observations. So every regression model that we've considered so far in this course has embodied the implicit assumption that the parameters are the same, that is, they're constant or stable for the whole sample. Obviously, this is in some senses a restriction and something that we'll be interested in testing. So for example, in the context of time series data, it may be that for half of our sample, one set of parameter estimates would be appropriate, but for the later half of our sample, a completely different set of parameter estimates would be appropriate. And that's clearly something that we need to examine in practice. And there are essentially two tests which we can use in econometrics, which will tell us whether our parameters are stable over the whole sample period that we've got over all the observations or not. And those two tests are called the Chow Test, which is sometimes also known as the analysis of variance test, and the predictive failure test. Now it turns out that both the analysis of variance test and the predictive failure test were essentially developed by the same person, Chow. So sometimes these are called Chow's first test and Chow's second test respectively. But for the purposes of this course, we'll call them the Chow test and the predictive failure test. Now both of these tests are essentially involved with trying to determine whether it's appropriate to estimate the same model for the whole sample of data, or whether in fact we really should be estimating different models for subsamples within that overall sample of data that we've got. But they approach this task in different ways. With the Chow test, we split the sample into two smaller subsamples and estimate three different regression models. A regression model for the whole sample and regression models for each of the two subsamples. With a predictive failure test, on the other hand, we only estimate two separate regression models, one for the whole sample and one for what we might call a long subsample. And with a predictive failure test, one way of thinking about it is that what we essentially do is use the regression for the long subsample and implicitly examine how well that regression model can predict the remaining observations in the whole sample that we didn't use in the long subsample. We'll come back to that point a bit later on, but first of all, let's have a look at the Chow test and see how that works. So just to summarise what I just said, with the Chow test, we estimate three separate regression models. All of those three regression models include the same explanatory variables and have the same dependent variable. So the value of k is the same for all three of these regression models, but the only difference between them is the length of the sample. So what we do is estimate three regression models and collect the residual sum of squares from each one. One regression model is for the whole sample of data, that is all the data that we've got in our sample, all the observations. Then we estimate separate regressions for two subsamples. Now we'll come on a bit later to the question of how we determine how big each of those two subsamples should be, but for now let's just assume that that choice has been made for us. Now again, as with many of these tests, there are a number of ways that we could perform the test. In terms of, for example, using either a chi-squared version of the test or an F-statistic version of the test. But for the Chow test, it's much easier to focus upon the F version, and that's what we're going to do now. If we think a little bit carefully about the formulation of the test statistic, then it turns out that whilst the test statistic for the Chow test looks slightly different to that of standard F-test statistics that we've calculated in the past. If we think about it in the right way, we can see a direct analogy between the Chow F-test statistic and standard F-test statistics that we would use to test any hypotheses. So what we want to do now is first of all to think about which are the restricted and which are the unrestricted regressions. In some way, this is the most complex part of understanding how the test works, and if we can understand what are the restricted and unrestricted regressions, then it's very easy in practice to actually estimate the test statistic and to understand why it takes the form that it does. So the easiest way to illustrate this is using a diagram. Let's suppose that we've got some set of data that we've estimated a regression model over, and let's suppose that it's a simple bivariate regression model so that we can plot it in 2 dimensions on a board. So let's suppose that we plot x2t on the x-axis and yt on the y-axis. And let's suppose that we have a scatter plot including all of the points. Okay, and again, in order to enable us to be able to actually draw this diagram in 2 dimensions, let's suppose that the sample split that we use for the Chow test also corresponds to a split that we use for x2t. I'll come back to that point in a minute. But let's look first of all at what we would have done given what we've learned so far on this course. What we would have done is taken these sample points and drawn a line of best fit through them. So let's suppose that we draw a line of best fit through all of those points, and the line of best fit is this black line here. Now, if we actually look at these points, it seems, given the way that I've drawn them, as if there seems to be a kind of split in the kind of pattern of the data, so that observations that are roughly to the right of this point here seem to follow a different pattern to the ones on the left. So let's assume that we split our data in half around this point here. Okay, and as I said, in order to be able to actually visualize this on the board in 2 dimensions, we need to assume that the split of the sample also corresponds to the split in terms of values of x2, although this might not actually be the case in practice. So let's suppose that we've got a sample of t observations where t equals 100. So our total sample is 100 observations. And let's suppose that this split of the data into 2 partitions the observations exactly in half. So we could then say we've got t1 observations, which constitute the first 50 observations in our sample, and t2 observations, which constitute the second 50 observations in our sample. Now, what would happen if we were to estimate separate regression equations for these first 250 observations, which correspond to the small values of x2, and then a separate regression for the last 50 observations, which correspond to relatively larger values of x2 because of the way that I've set this up? Well, if we estimated separate regressions, we might get something that looks like the following. We could estimate one regression model for the first half of the data, and maybe we get that red line there, and we estimate another regression model for the second half of the data, and maybe we get something like this. So these are the 3 regressions that we estimate. One for the whole sample, that's the black line, and one for each of the subsamples within the full sample, and those are the 2 red lines. Now, if we do that, we need to ask ourselves the question, which are the restricted and unrestricted residual sums of squares in each of these 2 cases? In other words, which are the restricted and which are the unrestricted regressions? Well, it turns out, in this case, that the unrestricted regressions are the 2 red lines. So, in fact, in this case, we have 2 unrestricted regressions. So we could say that this red line here and this red line there are both together the unrestricted regressions. And in fact, the black line is the restricted regression. So we can label this black line restricted regression. Now, why is the black line the restricted regression and the red lines, the two of them, the unrestricted regressions? Well, the answer is what we've done essentially when we estimate a single regression model is implicitly assume that all of the data are drawn from the same regime or from the same model. That being the case, we can see that we've implicitly imposed a restriction. We've imposed the restriction that all of the data must be drawn from the same model. That is, we've got a single equation for the restrictive regression which we force the model to fit for all of the observations. If we remove that restriction and we allow the two sets of data in each of the subsamples to be drawn from different models, that is to have different equations, you can see that that's a less restricted version of estimating the regression model than we had with the black line. So in fact, in the context of these Chow tests, we can think of the restrictive regression being the one that we estimate for the whole sample and the unrestricted regression as coming in two parts. That is, one for each of the two subsamples. So we collect the residual sum of squares from each of these three regressions, and we could call the residual sum of squares from the restricted regression RSS, okay, and we would call the residual sums of squares from the unrestricted regressions RSS1 for the residual sum of squares from this regression on the first subsample of data, and RSS2 would be the residual sum of squares from the regression estimated on the second half of the data, that is the second subsample. We then use those residual sum of squares to formulate an F-test statistic. Now, obviously, this is going to be the restricted residual sum of squares, and the unrestricted residual sum of squares is going to be given by the sum of RSS1 plus RSS2. The sum of RSS1 plus RSS2 will be the unrestricted regression in the F-test statistic. Now, if we were to think to ourselves, which will be bigger, RSS or RSS1 plus RSS2, well, the analogy with the standard F-test holds. That is, it's always the case that the restricted residual sum of squares must be at least as big as the unrestricted residual sum of squares. That is, we could write the expression RSS is greater than or equal to RSS1 plus RSS2. In other words, the residual sum of squares from this restricted regression must always be at least as big as the residual sum of squares for the unrestricted regressions taken as a whole. Now in practice, as usual, in practice we'll always find that the residual sum of squares for this restricted regression is bigger than the unrestricted residual sum of squares. So in practice this will just be a greater than sign in here, because it's always going to be the case that we get a slightly worse fit of the model, that is the residual sum of squares goes up when we impose the restriction that the data all has to come from the same model. And we can already see that if we just look back at the lines here. We can see that taken together, the two red lines here fit the data much better than the black line as a whole does. Because obviously the two red lines are able to fit to these separate parts of the data separately. But the black line is forced to fit to all of the data together. In the limit, we could ask ourselves, under what theoretical circumstances would it be the case that RSS exactly equals RSS1 plus RSS2? Well, the circumstances under which the restricted residual sum of squares and the unrestricted residual sum of squares are identical would be the same as for standard F-tests. That is, these two restricted and unrestricted residual sums of squares would be the same, only in the context where the restrictions are already present in the data. In other words, these two would be the same only if the estimated line for each of these two cases was exactly the same. If the estimated line was exactly the same for each of those two subsamples, that is, the intercept and slope for this red line was exactly the same as the intercept and slope for this red line here, then in that circumstance, obviously, the two red lines would fall exactly on the black line, and imposing this restriction wouldn't really be imposing any restriction at all. So in those circumstances, the two residual sums of squares will be the same. However, in practice, this is never actually going to happen. In terms of what hypothesis we're actually testing here, we can think of the hypothesis that we're implicitly testing being one that the parameter estimates are the same for each of the two subsamples. So let's suppose that, for example, our original regression model was yt equals beta 1 plus beta 2 x2t plus ut, where t runs from 1 up to 100. So this includes all 100 observations. We could then estimate our separate regression equations for each of the two subsamples. So that could be written yt equals alpha 1 plus alpha 2 x2t plus vt, let's say, where t runs from 1 up to 50. So this is the regression model we estimate for the first subsample here, and obviously we need to use a different notation for the parameters here because clearly they'll be different in general, and we also use a slightly different notation for the disturbance term because once again the disturbances in this model that's estimated only using 50 observations will clearly be different from this one estimated using all 100. So this will be the regression for our first subsample. We could then estimate another regression for the second subsample, and let's call the parameters gamma. So we'd have yt equals gamma 1 plus gamma 2 x2t plus, well, wt, let's say. And now t runs from observation 51 up to observation 100. The implicit restriction that we're testing here when we estimate the Chow test we could write as being that alpha 1 equals gamma 1 and alpha 2 equals gamma 2. So that being the case, we can see that the number of restrictions in that regression model is going to be equal to the number of parameters that we estimated in our original regression model. So if we go back to the formulation of the test statistic, we can see that in the second part of the test statistic, in the numerator, we've got t minus 2k. We know what t is. T is the total number of observations in our sample, which in this case is 100. In the denominator of that expression, we've got k. Well, in standard F-test statistics, we'd use the letter m to denote the number of restrictions that we were imposing on the model. Well, in this case, the number of restrictions that we were imposing will be exactly equal to the number of parameters that we're estimating in our original regression model. So clearly, in this case, we could write m equals k. So if we're estimating k parameters here, we've got one intercept and one slope here, for example, in our original regression model, then the number of restrictions we're testing is going to be equal to the number of parameters that we're estimating in the original model, because the restriction is that alpha 1 equals gamma 1 and alpha 2 equals gamma 2 across the two subsamples. Obviously, if I added another variable in here, I got plus beta 3x3t, then we'd have plus alpha 3x3t in here and plus gamma 3x3t in there. In that case, we would have k equals 3, and therefore the number of restrictions we would be imposing would be 3, because we'd add an and gamma 3 equals alpha 3 down here in that expression. So in the denominator of that expression, we've got k, the number of parameters we're estimating in our regression model. What have we got in the numerator? Well, if you remember back to our definition of the F-test statistic, we had t minus k divided by m. And the precise definition of k was that it was the number of parameters we were estimating in the unrestricted regression model. How many parameters are we estimating now in the unrestricted regression model? Well, the answer is now that unrestricted regression model comes in two parts. So if we've got two parameters in this restricted regression model here, in the unrestricted regression model, taken as a whole, we've got k in the first subsample regression and another k parameters to estimate in the second subsample regression. So in fact, the number of parameters we're estimating in the unrestricted regression model now is 2k, not k. So therefore, the part on the right-hand side of the F-test statistic is going to be t minus 2k divided by k. We've got k down here because we estimate k parameters in the original regression model, therefore that's the number of restrictions. We've got 2k over here because the number of parameters we're estimating in the unrestricted regression model is obviously twice the number that we had in the model for the whole sample because we've got two subsamples there. So that's why the F-test statistic takes the form that it does. The next question is obviously what distribution will that F-test statistic follow? Well, the answer is that the F-test statistic will follow an F distribution with k, t minus 2k degrees of freedom. That is, the critical value that we look up in the F tables will be have degrees of freedom equal to what's in the denominator here, what's in the numerator. So as always, we would calculate the value of our test statistic, we would look up the value of the critical value in the F distribution tables, and we compare the two. If the F-test statistic exceeds the corresponding critical value from the tables, we'd reject this null hypothesis here and conclude that the parameters in the model were not stable across the two subsamples. If, on the other hand, the value of the test statistic was lower than the corresponding critical value from the F tables, we will conclude that the parameters are structurally stable. In other words, the parameter estimates taken together here are not statistically significantly different across the subsamples. So that's how we calculate the test statistic, and that's how we interpret it. What would we do from a practical modelling point of view if we either rejected or not rejected the null hypothesis? Well, if we don't reject the null hypothesis, that means that we can not reject the assumption that the parameters are stable across the whole sample. That's good, that's what we want to see, and that would indicate that it was valid to estimate a regression model for the whole sample. So we can go ahead and estimate a single regression model for the whole sample. If, on the other hand, we reject the null hypothesis and we find that the parameter estimates are not stable across the two subsamples, that is, they differ significantly across the two subsamples, then in that case we would have to estimate separate regression models for each of those two subsamples. In other words, it would not, if we reject this null hypothesis, be valid to pool all of the observations together and estimate one model. We'd have to split them out and estimate two separate regression models. Let's now move and have a quick look at an example which shows how this thing works. So consider the data that we've got on the slide, and suppose that is for a CAPM first pass type regression model to estimate the beta for some stock, for example for the company GlaxoSmithKline. Let's suppose that we got data in our whole sample from January 1981 up to December 1992. And let's suppose also that we thought that the October 1987 stock market crash fundamentally altered the risk-return relationship in the markets. In other words, it fundamentally altered the beta of that stock. That being the case, what we could do is to split our whole sample of data into two parts around the October 87 crash. So the first subsample of data would be estimated from 1981 January up to 1987 October. Then the second subsample would be from 1987 November up to 1992 December. So we've got three regressions that we've estimated, and we've calculated the residual sum of squares from each one. Now, if we look at the parameter estimates in the two subsamples and for the whole sample, we can clearly see that they're different from one another. And of course, in practice, that's always bound to happen. That is, we're always bound to get slightly different parameter estimates if we use a different sample of data from within the given population. The question is, however, are the parameter estimates statistically significantly different across the two subsamples, or are they just a little bit different? Asking that question is exactly the same as saying, to what extent does the residual sum of squares rise when I move from a situation where I estimate two different regression models to a situation where I only estimate one regression model and I force the data to all be drawn from that same model. So once again, we can examine whether the parameters are structurally stable using this Chow test. If we now look at how the Chow test statistic is formulated, obviously we've got the restricted residual sum of squares, which is 0.0434. The unrestricted residual sum of squares is 0.0355 plus 0.00336, We then divide by the restricted residual sum of squares and multiply by the total number of observations t, which is 144, minus 2 times k. Now k in this case is 2 because again we've got a simple bivariate regression model, so 2 times k is obviously 4. And the last part in the denominator of that expression is k, the number of parameters we're estimating in the restricted regression model, and the number of restrictions we're placing on the model. Now obviously the restriction is that the parameter estimates are the same across the two subsamples, so therefore we've got two restrictions. A restriction that the intercepts are the same across the two subsamples and a restriction that the slopes are the same across the two subsamples. If we calculate the value of that test statistic, it turns out to be about 7.7. We compare that with an F distribution with k, comma, t minus 2k degrees of freedom. And k, comma, t minus 2k in this case is 2, comma, 140. So if we compare the test statistic with the critical value from an F distribution with 2 and 140 degrees of freedom at the 5% level, the value of that critical value is 3.06. So in this case we can clearly see that the test statistic exceeds the critical value, so we reject the null hypothesis at the 5% level. In other words, we reject the restriction, or we reject the null hypothesis that the parameters are the same in the two subsamples. So therefore, once again, if we had a result like that in practice, the implication for our model building is that we should not estimate a single regression model for the whole subsample, but rather what we should do is estimate separate regression models for each of the two subsamples. Another approach to examining parameter stability is given by the predictive failure test. Now, as I said, the main difference between the Chow test and the predictive failure test is that with the Chow test, we were forced to estimate 3 separate regressions. And in particular, we had to estimate regression models for each of the two subsamples. Now, in some circumstances, we might not have enough observations in each of the subsamples to be able to validly estimate a regression model. So, for example, suppose that we got k equals 8 parameters to estimate in our regression model, for example. And suppose that we'd only got, let's say we got 100 observations again in our whole sample, but let's suppose that we thought that the model may have broken down towards the end of our sample. In other words, suppose that we wanted to estimate the first subsample regression on the first 95 observations and the second subsample regression on the remaining 5 observations. Well, clearly in this case, we can see that that's not going to be possible. That's not going to work because in the second subsample, we haven't got enough observations to be able to validly estimate a regression model. Obviously, we need more than 8 observations in this subsample in order to be able to estimate a regression model with 8 parameters in it. So what can we do in that circumstance? Well, the answer is, in that circumstance, what we can do is instead of using the Chow test, we use the predictive failure test. So for the predictive failure test, we only estimate the regression model on the whole sample of data and on one of the subsamples, which we might call the long subsample. So essentially what we do with the predictive failure test is to split the sample in 2 again. We only estimate a regression model for the long subsample and for the whole subsample, for the whole sample, and not for what we might call the short subsample. Now, given that, there are 2 possible formulations of the predictive failure test. One is called a backwards predictive failure test, and one is called a forwards predictive failure test. To see what is the difference between these 2 formulations, consider the following. So let's suppose that our whole sample of data, T, included 100 observations. We could think of there being 2 types of predictive failure test. The first one we might call the forward predictive failure test. Now, under the forward predictive failure test, we'd estimate a regression for the long subsample T1, for example, that again might be 95 observations, and then we'd leave the remaining observations in what we might call a holdout sample, and implicitly what we'd be doing is saying, can the model, estimated using these first 95 observations, adequately predict the last 5 observations? So we could say there that T2 equals 5. So that would be called a forward predictive failure test, because we're estimating the model on the first part of the data and attempting to predict forwards the last 5 observations. The opposite case would be what we call a backward predictive failure test. And the backwards predictive failure test, as you can probably guess, would involve estimating a regression model for the long subsample involving the last 95 observations. We then attempt to backwards predict or backcast the remaining observations at the start, i.e. the remaining 5 observations. Now, when we've got 2 different types of predictive failure tests that we can calculate, we have 2 choices about the notation that we could use. We could either say, my notation is going to call the first subsample T1, whether it's the long subsample that we estimate the regression model over, or whether it's the short subsample that we're predicting over. But I think it's easier to use the notation that T1 always denotes the long subsample in the regression that we actually estimate the regression model over. And therefore, T2 would be the short subsample that we're essentially implicitly predicting over. So even though for the backwards predictive failure test, the observations in T2 come before the observations in T1, I think it's easier to use this notation. So in the notation that I use in this course and in my book as well, T1 denotes the number of observations in the long subsample which we estimate the regression model over, even if that long subsample actually comes second. So I think the reason that it's easier to use that notation is that, in fact, it means that we only have to use, we only have to remember one formula, and that makes our life much easier. So if we look at how the F-test statistic in that case is formulated, then the F-test statistic will be, again, very similar to the one that we would have for a standard regression model. The numerator on the left-hand side of the F-test statistic will be the difference between the restricted and unrestricted residual sums of squares. The restricted residual sum of squares would be the one where we use the whole sample of data. So the restricted residual sum of squares would be the residual sum of squares for the one that included all of the observations. The unrestricted residual sum of squares would be now the one where we had not forced the model to apply to all of the observations. So, for example, if we were doing a forwards predictive failure test, then RSS1 would be the residual sums of squares estimated on this regression model, including only the first 95 observations. If we were doing a backwards predictive failure test, then obviously in that case the residual sum of squares for the unrestricted regression, RSS1, would be the residual sum of squares for the long subsample in the latter part of the data period. The right-hand side of the test statistic is formulated by taking the number of observations that we have in the unrestricted regression, T1. So note that that's a difference between the Chow test and the predictive failure test. And we subtract away from that the number of regressors in the model. The number of regressors in the model for the restricted and the unrestricted regression, whether we're doing a forwards or a backwards predictive failure test, will always be k, the number of parameters we're estimating in the model. Finally, what restrictions are we imposing on this model? Well, it turns out the number of restrictions that we're imposing in the model is equal to the number of observations in the subsample for the holdout period. Now, we could write the null hypothesis for the predictive failure test as being equal to, as being given by, that the prediction errors for all of the observations in the holdout sample all being 0. So we could write the null hypothesis is that u hat t equals 0 for all observations in the sample T2. Okay? So implicitly, the null hypothesis that we're testing here is that the prediction errors for the holdout sample of 5 observations, whether we're doing a forward or a backwards predictive failure test, the null hypothesis is that these prediction errors are all 0. That's one way we could think of the null hypothesis being formulated. Obviously, we're then examining in a statistical sense how significantly different these prediction errors are. If the prediction errors are very different from 0, that means that the residual sum of squares between this unrestricted regression and the restricted one will be relatively big. If, on the other hand, the prediction errors are fairly close to 0, then the difference between this residual sum of squares estimated on the whole sample and this unrestricted residual sum of squares for the subsample, that difference will be relatively small if the prediction errors are small. That difference will be relatively large if the prediction errors are relatively large. So what distribution will this predictive failure F-test statistic follow? Well, the F-test statistic for the predictive failure test will follow an F distribution with T2, T1 minus K degrees of freedom. So if you're trying to remember what these degrees of freedom parameters are, they're always what's in the denominator of the test statistic, T2 in this case, what's in the numerator. And obviously, with the original F-test statistics, we had what was in the denominator m, what's in the numerator t minus k. So that's an easy way to remember what that is. If we now have a quick look at an example, to go back to our example of estimating the CAP-M type beta for GlaxoSmithKline stock, let's suppose now that instead of estimating a Chow test on this sample of data, we want to do a predictive failure test. So our regression model for the whole sample, that is all 12 years of monthly data, is the same as it was before. And the parameter estimates for the intercept and the slope were 0.39 and 1.37, and the residual sum of squares was 0.0434. Now let's suppose that we want to estimate a model on the first 10 years of monthly data, that is the first 120 observations, and we want to do a forwards predictive failure test on the last 24 months, i.e. the last 2 years of data. Our long subsample regression would therefore be estimated using those first 10 years of monthly data, so T1 equals 120. And let's suppose that the residual sum of squares for that long subsample is 0.042. So what we then do is to calculate the value of the predictive failure F-test statistic, and that would be given by the restricted residual sum of squares, 0.0434, minus the unrestricted residual sum of squares RSS1, which is 0.042, divided by 0.042, then we would multiply by T1 minus K divided by T2. T1 is the number of observations in the long subsample, which is 120. K is the number of regressors, the number of parameters that we're estimating, which in this case is 2. And T2 is the number of observations that we are implicitly predicting or we're leaving out of the long subsample sample, and that in this case is 24. So the value of the test statistic is 0.164. We compare that with a critical value from the F distribution with 24 and 118 degrees of freedom, and the value of that F critical value is 1.66. Clearly in this case, the null hypothesis that all of the prediction errors for the holdout sample are 0 is not rejected. So we conclude in this case that the model estimated using the first 120 observations could adequately predict the remaining observations, that is the last 24 observations in the sample. So in this case, we'd say that the parameter estimates are stable between the first 120 observations and the 144 observations for the sample as a whole. What does that mean? Well, that means in practical model building terms, it means that we can actually estimate the regression model validly for all 144 observations. So that's exactly what we want to find, and that's good. An obvious question now to ask is, how do we actually decide what the subsamples should be for either the Chow test or the predictive failure test? In both of the two cases that we've looked at, in both of the examples, I've made those choices very, very implicitly. Now, as a rule of thumb, we could do any of the following things. The first thing that we could do is to take the dependent variable yt and plot it over time. We would then split the sample according to any obvious large changes in y that seem to occur. Sometimes we call these large changes in y a structural break. So we plot y. It seems, if we look at the plot that I've given on the slides here, as if the pattern of y changes very drastically around about observation 180 in this sample. So that being the case, we could perform a Chow test where our subsample regressions are for the first 180 observations and then for the remainder of the observations starting at observation 181 towards the end of the sample. Now, just because there is a large structural break in y in our sample doesn't necessarily mean that the relationship between y and the explanatory variables will change. So just because y changes behaviour doesn't mean that the parameter estimates will significantly change. It might be that the change in y at observation 180 was caused by drastic changes in the explanatory variables of our regression model. And that being the case, the relationship between y and the x's will be the same, even though the values of the y's and of the x's has changed by quite a lot. So plotting the series y and looking at any large changes in y doesn't necessarily give us a good indication of where the relationship between y and the explanatory variables, which are the things that we're testing using these parameter stability tests, are actually changing or not. A second approach that we could use to determining where we should split the data for performing our parameter stability tests would be to go back to our kind of financial or economic history and ask ourselves the question of when important exogenous events actually happened. So, for example, there might be a stock market crash, a new government elected, a new type of trading mechanism like the introduction of the order-driven sets market on the London Stock Exchange. All of those big exogenous events, those big events that are likely to have influenced the time series of returns, for example, on those markets, those are the most likely events to have changed the relationship between variables. So we could use the dates at which those important structural events occurred in order to decide where to split our samples. Finally, we could just leave out the last few observations and run a forwards predictive failure test on those, or just leave out the first few observations in our sample and run a backwards predictive failure test on those. It's most likely in practice that our regression model is going to break down towards the end of our sample or towards the start and then to stop working again than it is to kind of break down in the middle and then continue working later on. So usually when regression models break down, they usually break down for good, and then we have to, in a sense, kind of go back to the drawing board and start again. Now, in practice, what we should do is to run as many different Chow and predictive failure tests as possible. And we can think of this as kind of throwing our model about a bit and kind of beating our model up, if you like. And if our model survives the beating that we give it, then the model is a good one. So, in other words, however many Chow or predictive failure tests we run using different splits of the data, if our model is a good one, it should pass all of those Chow or predictive failure tests. If, on the other hand, the model fails one or more of these Chow or predictive failure tests, we know that there's something wrong with the model. We know that the model parameters are not constant for the whole of our sample period that we've estimated the regression model over, and therefore we need to do something about that. Finally, on this topic, you'll note that the language or terminology which I've used to discuss the Chow and predictive failure tests implicitly suggested that we were estimating all of these Chow and predictive failure tests only in the context of time series regression models. But it turns out that the approach to using Chow and predictive failure tests could also equally validly be used in the context of cross-sectional regressions. So we could conduct Chow and predictive failure tests on cross-sectional regression models as well as time series models. All of the test statistic calculation, the critical values and how we interpret the result would all be the same whichever type of data we were using.